I promised you unlucky 13. I think I promised you unlucky 13. Let me move this over a little bit. Here we go. A lot of what we're going to be doing today is going to involve you solving really ugly equations. And trig on top of that is just like the cherry on the cake, top of the cake. We are going to, in question 13, we're going to find 8 intervals where the shape is concave up, right? So we're going to find out when it's happy faces, and we're going to find out when it's sad faces. And happy faces happen when the second derivative is greater than 0, right? When it's positive. And sad faces happen when the second derivative is less than 0. So the first job is to find the second derivative of this function. So let's get the ball rolling. This is a chain rule. It's a log of something. So you differentiate the log of something, you get 1 over that something. And then don't you finish with the derivative of the inside function, which in this case is cosine x. So the first derivative wasn't too bad. It's a cosine over a 2 plus sine x. Are we comfortable with that line? Right, nothing too surprising. Okay, now that's our starting point for the second derivative. Would you agree that this is an unavoidable quotient rule? Right, there's no way of not making a quotient rule. So I'm going to find the derivative of this guy, and it's going to be f dash g take away f of g dashed all over g squared. Now, once I have got this second derivative, and I've done all the style points I can get, so that's going to be, you know, make it look like the original, factor the heck out of it, and since there's some trig involved here, see if there's any trig identities that could simplify it. Once I've got this second derivative into as nice a format as it can be, we're then going to start hunting for when is the second derivative positive or negative. So here goes. The top guy's derivative is negative sine x times leave the g alone. Take away, leave the top alone and differentiate g, and differentiating 2 plus sine x gets me a cosine x. And then on the bottom, I get 2 plus sine x squared. Are we all okay with that? Right. Now, there's a fair amount of stuff I can do to this, so I'll start over here. That way it's at least going to be in the same page. I'm going to distribute, multiply through by negative sine x. So what that's going to get me is negative 2 sine x. This times this is going to get me negative sine squared x. And this times this is going to give me negative cos squared x. And the whole thing is going to be over 2 plus sine x squared. And now we're into style point territory. Don't do anything to the bottom. That's as good as it's ever going to be. Can anybody see anything in the top that could be simplified, put together and turned into something else? Because there is. So what is it? Okay, let's cover this guy up. Negative sine squared x, right? Negative cos squared x. That is equal to something.
It's a negative 1?
Correct. Now, you're not used to seeing it that way around, aren't you? Used to seeing it as sine squared plus cos squared is 1, right? That's the usual way you'd see it. But isn't the negative of sine squared negative of cos squared then negative 1? Wouldn't 2 sine squared plus 2 cos squared get you a 2, right? So don't just think of the basic one, right? The sine squared plus cos squared. Think of all the other ways you could muck about with it, right? In this case, you muck about with it by getting negative 1. And we are now finished with the second derivative. And there isn't really much more I could do to that to make it any prettier than it is. Now, since we are interested in the second derivative being positive and the second derivative is being negative, because that's where the concave up and where the concave down will happen, I need to get critical numbers. I need to find when is the second derivative 0, which means I now have to solve a really ugly looking equation. So here's a trick for you. If you have a fraction equals 0, you don't need to worry about what the bottom is. The bottom can be anything it likes. It won't make the answer 0, so you can ignore it. All you need to do is find out what makes the top 0. So we are now in trig world. I'm doing trig right now, and last 2 weeks ago we were doing solving equations, trig equations. So it's been a while since you've done it, but you solve trig equations, at least in the beginning, the same way you'd solve all equations. And that is, as long as you do it to both sides, it's okay rule. So can anybody tell me what I should do to both sides to get closer to the answer? What could you do to both sides here?
Add 1.
That's what I would do.
1, and then divide by 2.
Yeah, I like that. You want 2 or negative 2?
Oh, negative 2.
Okay, so you end up with that. Right, so when you do a trig equation, aren't you trying to get to sine x equals this or cosine x equals that? That's the usual thing you're trying to do. And then you bring this guy into play. And hopefully you can remember that the sine of an angle, I wish it wasn't called x, but it is, the sine of an angle, in this case, is the y coordinate. So if you want to solve when is sine x equal to negative a half, you want to find when is the x coordinate negative a half, right? So what kind of angles give me that? Didn't realize that was upside down. So I'm looking and I'm saying x. That's why that should never be called x. Call it theta, right? So I want the y coordinate to be negative a half. So I'm looking at places where the y coordinate is negative a half, and that's going to be the value of this missing angle. Okay. Can anybody see in radians an angle that has a y coordinate of negative a half? There should be 2 of them. A y coordinate.
Pi over 6.
So let's find your, right, would you all agree that's negative a half? So there's your first answer. Where's the other one?
11
Pi over 3.
6.
I hear pi over 3 and I hear 11/6. There's 11/6. I would agree with that one. I think the other one might be plus a half or something. So we have solved our trig equation. Now you see, solving trig equations start off very like an equation, but don't you finish with a unit circle typically? Now, technically, and I'm going to do it, even although I know there is no solution, aren't also critical numbers happen when the second derivative is undefined, right? And I have a fraction, this guy here, push it up a little bit more, I think. And I'm trying to find out when is this ugly fraction when is it undefined? Now here's the same kind of trick, but in reverse. When you know or trying to find when a fraction is undefined, it doesn't matter what the top is. It can be 42, it can be 0. It's probably not going to make any real difference. What is going to make a difference is that the bottom is 0. So when the bottom of a fraction is 0, you get an undefined answer, right? One that's not possible to calculate. Now, let's solve this one and then show you why you don't need to worry about it. If you take the square root of both sides, would you agree that 2 sine x has to be 0? And if you subtract 2 from both sides, you get that. Why does that not generate any answers? Why is there no angle where that's true? Try to phrase it differently. Can the sine x ever be equal to -2? No. Isn't the worst it can be is -1? You could argue, couldn't I look at this unit circle? Wouldn't I never find any place with a y coordinate of -2, right? So this generates no solution. But in a different question, it might. Can we pretend that said 1 plus sine x, just for argument's sake, right? If it had said that, wouldn't we be looking for that to happen, right? If that had said 1, right, we'd be solving this. This does exist, doesn't it? Isn't that going to exist at 3/2 pi? So you really should check when you have a fraction like this, that the critical number of when is the second derivative undefined, whether there are any. But in this case, there's not. So we can return back to, we now know the second derivative, so I'm just rewriting it again. And we have two critical numbers, 7/6 pi and 11/6 pi. And have I got my question anywhere? Well, I know what the answer that I should be doing here is. And we were told to only look in that region. Would you agree that's the only two answers that work in this region? Now, if they had changed this question from 0 to just pi, right? Wouldn't this one be ignored because it was outside the range, right? So when they say you can only use 0 to 2 pi, you get two answers. If they say you can only use 0 to say 1 pi, anything that's too big, in this case it would be that one, you would ignore. So be on the lookout in case the interval that they talk about isn't, oh, here we go, isn't just 0 to 2 pi, which it typically would be with a trig. Right, now we're moving on to what I call the table of signs. So we're going to have x. We're going to have, this time, the value of the second derivative. And then we're going to have shape. And it starts at 0, so I'm going to put a 0 there to make sure I don't go any further. And it finishes at 2 pi, so I'm going to make sure there's a 2 pi. And I'm going to go 7/6 pi, 11/6 pi, and I'm going to leave a space in the middle then. What would be a good value, and make sure it's some version of pi, what would be a good value to put in here? So it has to be between 7/6 and 11/6. What kind of pi could you put in there? 9/6, which is what, 3/2 pi? That'll do. Pi would have done, but 3/2 pi works perfectly fine. And then we go to our calculator, and I'm going through all the mistakes I have made in the past. First thing is I make sure that it is in radians, which it is. I don't know how many times I forgot to check and it's in degrees and I wonder why it's not working. Then y equals, in this case, it's a very ugly looking fraction. So I'm going to do a bracket. The negative, watch that, the negative button, negative 2 sine x. Take away 1, close the brackets. Then divide, start a new bracket, 2 plus sine of x, and square it. That looks good. And then I can go straight to table setup, delete all the answers from my previous question, And we should be good to go. So the numbers are going to be starting here, 0, 7, 6 pi. Yikes. How do you do 7, 6 the easy way? 7 pi divided by 6. That's probably the easiest way to do it. Then 3 halves pi, 3 pi divided by 2. 11 6 pi is 11 pi divided by 6. And finally 2 pi is just 2 pi. And the answers I get are negative 0.25, 0, 1, 0, and negative 0.25. These guys get me zeros. This guy is negative. This guy is positive. And this guy is negative. Now I like to draw a little number line. And I only put my critical numbers. Right, so that guy, put my 0 at the start and 2 pi at the end if you like. And my other critical number is going to be 11 6 pi. And it's negative, then it's 0, then it's everybody in here is positive, then it's 0, and then everybody here is negative. And this is very similar to what we did for increasing and decreasing, right? But when we did it with increasing and decreasing, it was the first derivative we're using. Now we're doing the second, but we use the information in a very similar way. You're going to be concave up, or you're going to be concave down. Concave up happens when the answer is positive. And so concave up is from 7 6 pi to 11 6 pi. Are we comfortable with that? Now, when is it concave down? It's concave down when the second derivative is negative. So in this region, and then in this region. And starting at 0 and going to 7 6, union, starting at 11 6 and finishing at 2 pi. Have you noticed that these aren't infinities? These are start and finish numbers, and that's because we were told to start and finish at 0 and 2 pi. And secondly, I don't know if WebAssign will allow this. I hope it does. Has anybody used the union symbol and it was happy with it? It took the answer. Right. It looks like the way WebAssign wants you to do this is you just type that guy in, comma, and then you type this guy in. Right. So this answer in WebAssign just looks like that, right? One interval, comma, the other interval, right? Now, if you've got time and patience, you might want to put the union symbol in just to see if it does it. Mathematically, that's actually a much better way to write the answer. But this is, I think, the software trying to make its life a little bit easier. So far, so good. Now, the last part of this question, because it is a long question, isn't it, asks us for the inflection points. I would call them points of inflection, but they're calling them inflection points. Inflection points are when sad faces turn into happy faces, that would be here, and happy faces turn into sad faces, that would be here. The thing about inflection points is that we've already found our answer. Inflection points happen at the critical numbers. So that's going to be at x equals 7 6 pi, there's going to be an inflection point, and at 11 6 pi. Now they don't want you to write down x equals 7 6 pi and x equals 11 6 pi. No, that's too easy. They want you to give the coordinates. And the original function, whatever it is hiding, which is this guy, you're going to have to use it. And essentially, the original function is this fella. So at the inflection point when x is 7/6 pi, the value of the function, which is essentially the y-coordinate, at 7/6 pi, is the natural log of 2 plus the sine of 7/6 pi. One of these unit circles is really indispensable for getting exact values. Don't plug that into the calculator and find out it's nothing 0.1234. Nowhere did they mention rounding things off. So if you don't see a 2 decimal place, you know you have to do it the hard way, which means it's going to be some ugly answer sometimes, right? They just are. Now, in this case, then, it's going to be the natural log of 2 plus the sine of 7/6 pi. If I find 7/6, which I know is floating around here, here it is, isn't the sine the y-coordinate? So it's that guy. And that guy becomes the natural log of 3/2. So the first one is 7/6 pi, the natural log of 3/2. Right, let's do the second one now. At x equals 11/6 pi, right, that's the other critical number. The value of the function, the original function, is going to be the natural log of 2 plus the sine of 11/6 pi. And it's pretty boring because it ends up being 2 plus -1/2 again. So it ends also being that. So they share the same y-coordinate. So the second one, that's the first one, is that coordinate. The second one has coordinates 7/6 pi, not 7/6, 11/6 pi. 11/6 pi, comma, the natural log of 3/2. And that would be us finished. And that took us 20 minutes. So obviously I can't do very many of them in a class period. Any questions about what we've just done before we move on to another one where I won't be doing quite as much detailed work? That's basically the template for how you find concave up and concave down. This one happened to have trig in it, but they don't all have trig. Okay, let's move on then. The next one is also got log in it. This is going to be question 14. And I'm only going to take this question part of the way. So we're being asked again, concave up, concave down. So first derivative, the natural log of something, 1 over something, times the derivative of the inside function. So the first derivative ends up being that guy. To get the second derivative, it's going to be a quotient rule. So f dash g, take away f of g dashed over g squared. Differentiate the top, you get 2, leave the bottom alone. Leave the top alone, and differentiate x squared plus 2, and the whole thing on the bottom, squared. That's 2x squared, take away that, so you get 4, take away, what's that, 2x squared, yeah. Take away 2x squared over x squared plus 2 squared. So that's what the second derivative looks like. Let's find the critical numbers. I'm not going to bother about anything being undefined because x squared plus 2 will never be 0. So I'm only going to look for critical numbers when the second derivative is 0, which means I need to solve When is this thing 0? But just like last time, if you have a fraction and it equals 0, only the top needs to be looked at, in which case we're here. What should I do to both sides then to solve this?
Subtract 4.
Okay, so negative 2x squared is going to equal 4. Oh, negative 4. Divide both sides by negative 2. Okay, where do we go now?
Goes root 2.
Okay, and you're going to get a negative square root of 2 and a positive square root of 2. There's your two critical numbers. Okay, build your table of signs and do all the other stuff and you're finished. Okay. And for the last question from this section, I'm just picking one question and we're going to do everything. We're going to do increasing, decreasing. We're going to do local max and mins if they've got any. We're going to do concave ups, concave down, and inflection points. Oh, by the way, won't this shape maybe have 2 inflection points, right? 2 critical numbers could have 2 inflection points. So the last one of this section is going to be question 17. And here goes. Just clearing some paper up. Pretty much putting everything that we've learned over the last few days together. So I'll start with the first derivative because that's going to tell me increasing and decreasing. And I get a 2x, take away 1, take away 1 over x. Agreed? Now, let's look for critical numbers. Are there any values of x where this expression could not be evaluated? Because I can see one and only one answer. Can anybody see a problem?
X equals 0.
Okay. Would you agree that's just looking and you can say fractions can't have 1 over zeros in them, right? So that's why I picked up. Normally undefined are kind of easy to see because a lot of the time you don't have one. And when you do have one, it's kind of obvious what it is. On the other hand, you have to do equations very often to solve this one. So I need to solve when is this ugly equation equal to 0. And I promise you at the start of today, you're going to have some ugly equations to solve. As long as you do it to both sides, it's okay, Rome. I don't think we've ever done an equation that looks like this before. So you're kind of out there in unknown land, unknown territory.
1x on the other side.
I didn't catch the first part of what you said, so it may be correct, but I didn't catch what you said.
Put the negative 1x, move that over there.
Okay.
Take it 2x minus 1 equals 1f over x.
Correct. That's exactly what I would do. You're on the right tracks. Anybody want to help them out with the next step? I'll give you a clue. Anybody want to help them out with the next step?
I see it. Yeah.
Okay, go for it.
Multiply that x to the other side.
Sometimes called cross multiplication. Okay, anybody want to take us to the next step? Right. What should we do next?
I think we're already there.
Well, almost, but don't try solving it yet. You still have a little bit more work to do. What should we do with this left-hand side?
Looks like we'll have to FOIL it.
Okay, correct.
So I'm thinking two.
Then subtract 1. Now, if you were looking at that and you were saying, oh, I got the answer, it's 0.5. That would only be true if this was equal to 0. When this is equal to 1, you really don't know what x could be. Now we have a quadratic. We're going to factor it. Any obvious factors that could work with this guy? Any volunteers for combinations that would work in this case?
-2
Wait.
and 1.
So -2 here and 1 there. Or do you want a negative? No. Take that back.
2x plus 1x minus 1.
Yes. That might be the final answer as well. So -1x plus 1, right? That's the one that works. And from that horrible mess, which I'm now going to fold away so it doesn't distract me, we can now get our critical numbers. It took us long enough to get them. There they go. So we now can move on to the table of signs. And we have an x. We have a 0 and a 1. And we don't have that. That's -0.5. I'm prejudging my choices. First derivative, shape. I'm going to write that again. That's better. So I have to pick a guy here, a guy here, a guy here. I'm going to pick 0. I'm going to pick 2. I'm going to pick -1, right? Make life easy. I have the derivative. I guess I'll write it up here because it's a little bit ugly. Couldn't really do much in the way of style points with that. So clear this out of the way. Y equals, and it's going to be 2x, take away 1, take away 1 divided by x. Then I'm going to go into my table, clear out the old stuff, and go -1, -1/2, 0, 1, and 2. And the answers I get were -2, 0, and I darn well should be shot. I missed 2 guys that I need. So I forgot all about the 0. That's what caused the problems. That's okay. That's undefined. And I know that's, what's that, the other answer? That's 0, right? So I'm just going to go back into my table. And start again. -2, -1/2. Then I need somebody in here. So I'm going to have to pick some like -1/4, which isn't pretty. Then I'm going to do the 0. Then I have to squeeze somebody in here. So I'm going to have to call that a 1/2. And 1. And finally 2. Okay. When x was, oh, I don't have -1 in here anymore. When x is -1, you get -2. That's good. You get 0. At -1/4, I got 2.5. At 1/2, I got -2. And at 2, guess I'll type that in because I can't see it anymore. I get 2.5. So I got a negative, a 0, a positive, an undefined, a negative, a 0, and finally I got a positive. So my critical numbers were at -1/2, at 0, and at 1. And here I get a 0, here I get undefined, here I get a 0. Everybody here is negative, everybody in here is positive, everybody in here is negative, and everybody here is positive. So I'm now going to get, when is it increasing? When is it decreasing? It's increasing from here to here. So that's from that's from -1/2 to 0. And here, forever. So that would be from x equals 1 to infinity. And it's decreasing over here. So that's -∞ to -1/2. And between 0 and 1. Are we okay with increasing and decreasing and whatever? Provided I did this question correct, which I'm hoping I did. If I look at this shape, let's see if we can get the shapes here. It goes negative, zero, positive. If I look here, it goes positive, 0, negative. And if I look here, it goes negative, 0, positive. And I have just discovered something that hasn't happened yet. Remember the original function? The log of x doesn't exist everywhere. You can't get logs of negative numbers, which kind of means that this side of the table doesn't even exist, which means that my answer to increasing and decreasing only uses this table. 0, 1/2, 1, and 2. And the value of the derivative is undefined, -2, 0, and positive 2.5. So it's undefined, negative, 0, and positive. Which means I only have, I'll draw my little line here. I only really have a couple of places where I need to look. I got this guy here at 1. So everybody over here is negative, and everybody over here is positive. So my function is increasing from 1 to infinity, and it's decreasing from 0 to 1. That was sneaky. I mean, the math said that the points up here, theoretically at least, would exist. But since the function log x doesn't have a value in these regions, these were totally ignored. And I'm having a quick look in case they warned me in the question and I didn't check it. No, wouldn't it have been nice if they had just said x greater than or equal to 0? Wouldn't that have just made me think about it a little bit more? Well, in that case then, based on this shortened version, I have a negative, a 0, and a positive. So I have a local minimum at x equals 1. And its coordinates are 1, 0. And so you would write down as your answer to the local min, which is part B, local min. You would just type in the y coordinate, just that guy. And then it asks for a local max. This shape doesn't have any, so you just type in DNA. So that's what the two answers in B would look like. Rushing here a little bit, I apologize for that. We know that the first derivative is this guy. And to remind myself, you can only use x's that are greater than or 0. And I'll now find the second derivative. This guy is 2, this guy is nothing. And if you want to differentiate 1 over x, you call it x to the negative 1. And if you call it x to the negative 1, you get basically that guy. So let's go for critical numbers. When is the second derivative undefined? And the answer in this case is at 0. When is the second derivative equal to 0? Well, that guy has no solution. 1 over x squared is always going to be a positive something. 2 plus a positive something can never be 0. So there are no solutions. So there's only one critical number, and that is at 0. And our table is going to be very boring. You have to start at 0. You can't pick negative numbers. And then my other guy is going to go there. I'm going to do my second derivative. And then I'm going to do shape. So it's going to be a tiny table. At 0, it's undefined, so undefined. And at 1, well, if you plug in 1 here, you get a positive 3. So what does that tell me about my shape? Call that 0. Call this guy 1. And basically, everybody is positive. And so this thing is concave up from 0 forever. And what about concave down then? Just making this on time. It's never concave down. Whew. Just made it. Perfect timing. So put your last name down for attendance and call it good. Sorry about the little hiccup there. These numbers, just to remind you, are not usable because the log function can't be used for negative x's. So we ended up with a very small table and an even smaller one when you did second derivatives. And bye-bye from now. I'll hang about for any questions.
Thank you.
You're welcome. Bye-bye.
I just have a quick non-math related question. I got here pretty late, something came up today, but I remember you saying something at the beginning of the quarter that you record them and post them on Canvas, I think? That
Yes,
I
they
can
do.
watch
You
this
can-
class a little later?
Yes, you should be able to do that. And that goes for anybody, especially if we cover a lot of work. You might say, I know he said something, but for the life of me, I can't remember what he said. You know, just go back and have a quick look at the video. You can fast forward, you know, and jump to the bit that you think, you know, beginning, middle, end.
Okay,
Do
perfect.
it
Do
that
you
way.
still want me to put my last name?
Yeah, you're essentially here. You tried. I'm assuming there's a good reason you didn't make it on time.
Yes, sir.
I don't need to know it, but I'm assuming it's a good reason.
Alrighty, thank you.
Okay, bye-bye.
Bye.
Have you got a question for us? No? Then I think we're out of here. Rowan, do you have a question? Okay, bye-bye for now. See you tomorrow.